Shape of the universe. The question of the universe's shape is as old as our curiosity about the cosmos. In ancient times, people often imagined the earth as flat, forming the central foundation of the universe. Yet, as early as ancient Greece, philosophers and scientists began challenging this view. They recognized that the earth is spherical and even estimated its diameter with remarkable accuracy. This insight stemmed not only from keen observation, but also from the influence of Greek geometry, which regarded the sphere as the most perfect and harmonious shape. With the rise of modern astronomy, our view expanded dramatically. The Earth was revealed to be just one planet orbiting the Sun. The Sun itself turned out to be one star among hundreds of billions in the Milky Way. Powerful telescopes then push our vision further to the edge of the observable universe. We now know that there may be between 200 billion and 2 trillion galaxies like the Milky Way in the observable cosmos. Yet this observable universe is only what we can see. Because light takes time to travel and space itself is expanding, any galaxies beyond this observable boundary are forever hidden from us, not by limitations in technology, but by the fundamental laws of physics. It is therefore likely that what we can observe is just a small region of a much larger and possibly infinite universe. Space as substance, not emptiness. In Newtonian physics, space was treated as a passive, empty stage, a backdrop in which matter moves. It was modeled as flat, using Cartesian coordinates. Even in Einstein's general relativity, which allows space to curve in response to mass and energy, space remained a kind of geometric scaffolding. The shape of the entire universe was not dictated by the theory itself. However, from Einstein's equations, cosmologists derived the Feynman equations, which described how the universe expands. These equations suggest that the overall shape of the universe depends on its mass density. If the density is low, the universe is hyperbolic and open. If high, it becomes spherical and closed. A special case, precisely balanced, results in a flat universe. Current astronomical data suggests that the universe appears flat or extremely close to flat, though this conclusion is based on observations within the limits of our detection. The world membrane hypothesis. In the theory of world membranes, the universe is not an abstract space, but a real physical entity, a membrane that curves through higher dimensional space. This theory asserts that the universe has a definite shape. It is a three-dimensional spherical surface, closed and finite in size. This is not a speculative assumption. It is a prediction, one that can be tested with higher precision observations in the future. The geometric justification and amplification of this spherical membrane are detailed in Volume 4 of the Universes Are Black Holes series. To understand this concept, imagine the surface of the Earth. It is a two-dimensional sphere embedded in three-dimensional space. Analogously, our universe is a three-dimensional spherical surface, likely embedded in 4 or more spatial dimensions. Just as we do not notice the Earth's curvature in daily life because its radius is so large, we experience our universe as locally flat. This is because any small patch of a vast sphere appears flat up close. However, the global geometry matters. A spherical universe is closed and finite. It curves back on itself. And just like Earth's surface isn't perfectly smooth, the three-dimensional sphere of our universe may contain local deformations, regions of warping and curvature that give rise to complex structures we observe. Humans were not born just to survive. We were born to think, to drive. So when we ask, what is the universe? We are also asking, who are we? Let's explore the child's perspective of the universe together.
Beneath the vault of endless skies, I tread where ancient starlight lies. The universe, a boundless sea. I am its voice, its destiny.